This is Physics 2211, Lab 2, Projectile Motion. So the purpose of this lab was to model the motion of an object that is thrown using differing degrees of accuracy and compare it to the real-world data that we collected in the lab. The fundamental physics principles that were used were Newton's second law and gravitation near the surface of Earth and drag force. So Newton's second law is obviously the sum of the forces equals the mass times acceleration. Gravitation near the Earth's surface, I'll talk about on the next slide, and also same with drag force. The main physics ideas, so Newton's second law gives us the velocity update formula, which is shown on the left, and we can get the position update formula from that. And then gravity near the Earth's surface is about 9.8 meters per second squared, and we can get that using the equation that says the force of gravity is equal to negative g(m)m over r squared. And then since air particles in the atmosphere slow our object down, we also have to consider the drag force in this situation, which the equation is given on the right. The system in this experiment was the paper ball. The surroundings were Earth, the air, and anything else that exerts a force on the ball. And then in the middle, we can see the free body diagram of our ball. We have two forces acting, gravity and the drag force. The drag force is going to be a bit smaller than the gravity. Okay, a brief preview of our results. The more forces that we added to our computational model, the more accurate it got, and the model that considers drag and gravity is more similar to our observed data than the one that only considers gravity. Here is the video that I put into Tracker. As you can see, the y-axis is just along the side of the video, and the x-axis is lined up with that meter stick on the table. And there is our paper ball as we threw it across the table. So our data taken from the tracker, our start time where I started the tracker was 2.3667 seconds. The end time where I ended the tracker was 2.6 seconds, which is right where it hit the table for the first time. The time interval between the distances was 0.033 seconds. The ball mass was 0.045 kilograms, and the initial position is listed there, and so is the initial velocity. I took the initial velocity by finding the average velocity between a couple of the points in the tracker data. This is the code for the model that only considers gravity, and the changes I made to the starter code were line 46, I added the mass of the ball, lines 49 and 50, I added the initial conditions of our of velocity and position found from the tracker. Lines 53 and 54, I added initial time and the time step. Line 59, I added gravity. Line 74, I added final time. Line 79, I calculated the force, and lines 82 and 83 were the position and velocity update formulas. This is the code for gravity plus drag. I did all the same changes that were mentioned in the previous slide, plus in line 63 I added the B value for drag calculations. Line 79 I calculated drag, and line 80 I added drag into the net force calculations. Everything else is the same as the previous slide. So this is the output graphs for each model. With drag is on the left, without drag is on the right. They are slightly different. As you can see, the with drag model is a bit steeper at the beginning, and yeah. So here is our graph of both of our computational models plus the observed data that we collected in class. So obviously there are differences between the model and the observed values. The observed graph does not move in perfect parabolic motion, which might suggest that different forces might be acting on it. The graphs all have the same general trend though, so it's obvious that our computational models were correct in plotting the general trend of the motion. Some possible sources of error that can account for these differences are differences in placing the center of mass in the tracker, and rounding errors, and errors in determining the drag coefficient. For the discussion questions, the what does it mean question was, do any of our models predict terminal velocity? The answer to that is no. There's not enough time for the object to reach terminal velocity. It would have to be falling for a lot more time to be able to have that drag catch up to the force of gravity and be equal to it. And an experiment that might reach terminal velocity is if we dropped an object off of a really tall platform, because that would allow the object to be falling for enough time to be able to reach terminal velocity. And then the what if question was, what if we threw the ball straight up? Would the time it takes to reach the ground be the same? And the answer to that is yes, because also the question mentioned it having the same velocity as when we threw it in the experiment. So the time it takes to reach the ground would be about the same, since the ball would still be acted on by the same forces, therefore making it reach the same height and falling from there. And obviously we can determine the time it takes in the air by the height and the forces that are acting upon it. Okay, so that's it. Thank you very much.